We have Dr. Sebastian Geiger from TU Delft to talk about reservoir modeling for the energy transition.
So thank you very much for having me here and speak. And I just want to come back to one of the points that Marcos made, the human capital, innovation. This is key to managing the energy transition. It's really great. And Hardy and I spoke about this. But it's really great to see the innovation and the compassion and passion from the PhD students here in the summit. I think none of us chairs would be here without the PhDs. So I want to talk about reservoir modeling for the energy transition. What you see is a picture from the TU Delft campus, the geothermal wells that we've drilled a while ago. I think I can go now and we can close my talk because Hardy took away my punchline, which is, I'm a reservoir engineer, I need to understand geology. So clearly, Hardy, I've polluted your thinking way too much. We can break now, go for a beer, and then have a coffee break. No. So the point I want to make is we need to bring geoscience, geology, and reservoir engineering closer together in the energy transition. And some of the tools we love to use in the oil and gas industry don't quite work as we expect them to do. And I try to point out the work on the PhD students along the way, but there are also other people outside TU Delft, Carl Jackman, Matt Jackson, Gary Hamstrom, Peel College London, Phil Ringrose, Mark Bentley, Pat Jackson, Alad Martinius, whose thinking and their work has really influenced the story that I want to tell here. So what we're interested in is low-carbon geoenergy, so geothermal energy, CO2 storage, cyclic hydrogen storage, and how we model the reservoirs and the dynamics in the best possible ways. The EU has actually set some clear targets for scaling up these technologies. So 25% for heating, 10% for electricity production in terms of geothermal energy is one of the biggest sources of CO2 emissions in the EU. With space heating, about 18% of the total CO2 emissions in the EU is for keeping our houses warm in the winter. CO2 storage, yesterday we heard a lot about war on carbon, about CO2 storage, Longship project, Northern Lights project. The EU wants to store 280 million tons of CO2 by 2040, so we need many, many more of these projects. And Hardy spoke about geomechanics, geometry, and geology again, about cyclic hydrogen storage with targets for in the EU as well. Yesterday we also talked about Kenya, came up in the war of carbon. This is a picture of the Olkaria geothermal power plant, where 40% of the electricity demand in Kenya comes from that one geothermal power plant with additional benefits for clean and direct air capture, etc. Energy poverty in Africa and the neighboring countries is still quite high, 50%. Uganda, 50% in Tanzania of the population don't have access to electricity. They sit on the same right geological conditions in the East African Rift that can really help to alleviate energy poverty through geothermal energy. So, problem is everything happens deep underground. Geology, we have some happy geologists there and an outcrop, and even the non-geologists see there's some geological heterogeneity in there. We zoom out a little bit, we still have where that red arrow is, our happy geologist. What we do in reservoir modeling, we slap a grid on this, have these football-sized, in terms of aerial extent, grid blocks where we then assign a single property, run our reservoir models, and sort of predict an outcome. And what common theme there is this idea of lost heterogeneity. So we build our reservoir models, we have seismic data, we get the big reservoir structure, the key horizons, we run some well logs, we get a running average of some petrophysical properties. We block these well logs, we then lose even more heterogeneity and assign reservoir zones. And then we have our lonely core plug and the size of a flashlight battery where I do some petrophysical tests, get the rel perms, capillary pressures, permeabilities, porosities, some rock strength, and then you use this data from this tiny little block to basically populate grid blocks of the size of a football pitch with their properties, with the petrophysical properties. So we lose a lot of heterogeneity in that process. And even in the core plug, so this is the experiments we did with Kamal Singh and Zai Jangda at Herdwat University. There's a mini core plug. It's a cyclic hydrogen storage experiment. The red colors show the distribution of hydrogen in that core plug, and there's a tiny little layer that is a little bit less porous in the center, and you can see actually in these different pictures how that little bit of heterogeneity impacts the trapping and reconnection of hydrogen during imbibition in drainage. Now, in oil and gas reservoir modeling, so we know that we lose a lot about the heterogeneity in our workflows. Yeah, and then we do the history matching, blame the geologist for not having given us the right geology, and we tune the parameters, and we get a good match, and off we go. Mark Bentley came with this really great analogy that I love, and there's one thing we can remember. It's trying to build an aeroplane where we break the one wing because we don't get the right geology into our models. And all we do is we break the other wing by having a model that's a really poor representation of the geology, put various parameters, dial up and down various parameters. That little red blob there is, in that real reservoir model, probably the worst crime they've done to get a good history match. You have two broken wings. That sort of should equal each other out, and hopefully the entire plane is going to take off. If we go, and there was an independent project audit in 2012, and they reviewed 150 offshore oil and gas projects. What they found, 73% of these oil and gas projects never delivered to plan. Most of the projects had actually negative NPV under saved by oil price, and over 50% of the projects where they had problems were due to issues with geology. Reservoir was more compartmentalized than they thought. The sand wasn't as continuous as they thought. Oh, the permeability distribution that we had were actually worse than the worst case assumption we had in our models. And the point I want to make, if you think about low carbon energy, geothermal, CO2 storage, hydrogen storage, we cannot afford this. This is geothermal example. Top left picture is from Landau in West Germany, in the Rheingraben. What you see is a ground uplift, red color shows of uplift about rates about 3 to 4 millimeters per year. That project was stopped because, not of the risk of induced seismicity, but because of the uplift in the vicinity. Collecting more data in a geothermal environment is really tricky. This central picture is from the city of Munich in Germany, where they've done 3D seismic. They've run these virus trucks up and down the streets. That's not really fun for the neighbors. We drilled on campus, or well on campus in Delft. That's a noisy undertaking. And any project that is not successful, that doesn't deliver to plan, we're not even talking about induced seismicity, earthquakes, or the things that can really go wrong, just a dry well, that does make the local population unhappy because we typically sunk money from public money, public funds in these projects, and we lose that trust that actually geothermal energy, CO2 storage, hydrogen storage can shift the needle in terms of reliable, affordable, secure energy supply in the future. This is an example of geothermal energy. In Marco's talk, we heard about CO2 storage offshore Brazil, and Hardy and I, we have really the pleasure and honor to work with two Petrobras employees who have been seconded to us to do the PhD on CO2 storage at TU Delft. And they have so the small task of trying to find the best storage location in an aquifer in the Santos Basin, about the size of the Netherlands, start injecting CO2 for some of the big emitting sources in Brazil, and sort of integrate geoscience engineering to find the best solution, the best location for CO2 injection. Coming back to our picture here, that's the outcrop picture. Basically what Felipe and Matthias have to do is sort of find in this really big model that somewhere is that local geological model, that local heterogeneity that you see in the outcrops is somewhere hidden in there, and trying to make a good prediction where to start injecting CO2. So what do we try to do? We need agile workflows to build meaningful geological models for the energy transition faster. We also need to think about how we screen for good, promising project locations in an effective way. So to find these class A, the next projects where we want to invest our resource in characterizing them to make geothermal energy, CO2 storage, etc. happen, because we really need to scale up these activities. We need to think about lost heterogeneity, how we work across these scales, how we transfer information from the smaller scale to the larger scale in these big reservoir models. And Rick sort of alluded to this a little bit in his talk as well. What's the most valuable data? What's the data that we want to acquire that really shifts the needle in terms of being able to operate projects efficiently, cost-effectively, and securely? I'm not going to talk about RM. I've bothered you in previous summits enough with RM. If If you want to learn more about screening, go and visit Anna's post. Has done some really nice work on how to screen potential storage site for offshore hydrogen storage in the depleted gas fields in the Netherlands. Screening for CO2 storage, go and talk to Felipe, who has a really nice poster on this work in the Santos Basin in a partnership with Matthias. And in terms of screening for fractured geothermal reservoirs, go and have a chat with Ellie, who's looking at how you can use very early dynamic data from well tests to identify key fracture properties, what they could mean for the success of a geothermal project later on. I want to spend the remainder of my talk discussing a little bit about the lost heterogeneity and how we can transition information, geological information, about scales. Because remember what Hardy said, the punchline is we need to know our geology. The challenge is we have, again, our core, the little plugs, we measure our properties, and then somehow we have this belief that what we measure at this scale, so we can apply it to a reservoir model where a grid block is the size of a football pitch. And in between, we have all these different geological concepts and models where we have additional heterogeneities. And the question is, how do we get these heterogeneities from one scale across to the other scale? Now here is a challenge for Rick, the elderly statesman of the, he's looking up there and is really worried, the elderly statesman of the energy simulation chairs. Shanti Chandra, a PhD student of mine, back in 2013 presented that work actually at Energy Simulation Summit, Duke. There's also the challenge for you if you remember this. This is real data from a real carbonate reservoir. You can't really see this on that core plug there, but there are many parameter measurements, and the permeability changes in sort of a centimeter scale between somewhere 200 millidarcy and 0.1 millidarcy. Lots of heterogeneity. The problem for this extreme variation in heterogeneity and permeabilities, there was a lot of corrosion happening, and there's an entire geological history why this corrosion happened. But the problem was that when they sampled the permeability, the cores, measured the permeability, they came up with a pore-perm transform that you see on the bottom left picture that was way too low because a lot of that more permeable core broke away, and they couldn't do the porosity permeability measurements. So Shanti found a way how you incorporate these next scales of heterogeneity, these smaller scales of heterogeneity into reservoir, rebuild your poro-perm transform, and everything suddenly shifted to higher permeabilities. We then do a history match, and you compare cumulative production as a function of time. The top line is historical data, and we have the new transform so that porosity and permeability are shifted to higher values. We get a really nice agreement without even history matching. We took the old transform, that's a dashed line on the bottom, the light gray lines are different geostatistic variations. Really, the operators really couldn't get a good history match. So getting the right geology into our models, knowing the geology, really helped to constrain history match and constrain uncertainties. And that model on that broken airplane wing, that comes from this one. And as I said, that block is the worst offense. It's not even the worst offense in a reservoir model. They're big squares of uniform permeability. They're donuts around individual wells to get the wells to match the production data. So 2 wrongs doesn't equal 1 right. Loss heterogeneity also matters in CCS. Again, Marco said in the pilot plant, solubility trapping, residual trapping, key aspect for storage security. This is a really nice recent review paper by Ni et al. That discusses the influence of capillary heterogeneity on CO2 storage. What you see are experiments for sort of ripple lamination and cross lamination. There's a scale bar, so they're about 50 centimeter horizontally in size. And towards the right, the heterogeneity starts to increase. You see it's very different, and colors show the non-wetting phase saturation, so the CO2 distribution. So as we increase heterogeneity, as we change the complexity of the heterogeneity, we get very different small-scale saturation patterns that ultimately are going to tell us how the CO2 is being trapped by residual trapping, by capillary trapping, one of the early lines of defense during CO2 storage. And that's something we don't capture easily in our large-scale reservoir models. Certainly not in the models that Felipe and Matthias are working on that are hundreds of kilometers in size. How do we translate that information across scales? How do we deal with this lost heterogeneity? Rick talked about stress path. Giovanni talked about fault reactivation. We really have to deal with some complex physics in these low-carbon geoenergy applications. Deformation, we have depleted reservoirs to now inflate again. We have chemical reactions. So these coupled chemical, hydraulic, mechanical, thermal effects. How do we transfer for complex physics, geological informations across scales? What geology matters in our models? What it all boils down to is the representative elementary volume. So typically we draw permeability as a function of scale, and the REV, representative elementary volume, changes as a function of scale as we sort of increase measurement scale and we pick up bigger and bigger scales of heterogeneity. And then there's the scale gap between the logging tools and the well test and seismic data, where somewhere in there sit our grid blocks. We know there's a lot of heterogeneity that we can't really deal with easily in our reservoir models. I would argue that if you come to porosity, we sort of know how to assess REVs. Permeability, yeah, we sort of know this as well, as long as we don't have to deal with complex fractures. It's good. It's really fishy is once we go to two-phase flow, and God help us, mechanical properties. Rick has done some really nice work on upscaling, but I asked him yesterday, do you know what the REV is for mechanical properties? And I think I got a shrug with a shoulder there. So more complex physics, we don't know what the REVs are. So this is one of the research lines we're currently playing around with, and there are people like Jesse Steinfort and Anna Lodwert who are looking at these challenges. So go to outcrops. We use RM to build outcrop models. We distribute porosity and permeability from subsurface data sets, and then use RRM to immediately upscale, calculate effective permeabilities for these outcrop geometries. If we change the scale of these models, if we take submodels, we look at how that impacts things like the effective permeability workout. At what scale can we upscale average permeabilities properly to identify RV scales? And the idea is that when we then start building reservoir models, we no longer take these little core plugs to populate grid blocks, but we actually take geologically informed properties to rebuild the reservoir models. And one of the really nice things, and again, Rick alluded to this in his talk with the Aquistore project, there is no open access data from real reservoirs for CO2 storage, geothermal energy. This is from the Groningen gas field in the Netherlands, where they had a lot of issues with subsidence and use seismicity. We have these data sets, so we can actually use all these really nice new workflows to rebuild the models and test, do the new technologies really shift the needle in terms of how we think the reservoir is going to behave? Would we make reservoir management decisions in a different way if we would have used today's technologies in the past? In terms of lost heterogeneity, this is work that Shakawat Hossain at Imperial College London has done. We've contributed a little bit to this. So we have no workflows. This is for the Bunter sandstone, one of these big sandstone formations in the northern part of Europe, in the North Sea, that's used for oil and gas extraction, CO2 storage, geothermal energy. So we have no workflows how we can identify these RVs. You see on the left-hand side, so they are core images. We know from the core images what are the geometries at the next larger scale are from outcrop analogs. In RM, we can then very quickly build different representation of these typical heterogeneities that we find in geological formations such as the Bunter sandstone. Here's one example of some cross-bedding. And then we just simply resize these models in the strike direction, dip direction, vertical direction, see what happens, for example, to the permeability in the three directions. And when will the permeability value stabilize? It tells us something about what's the right REV scale. One of the things you also see is that we have arithmetic means and harmonic means, which you always teach a student. Flow parallel to layering, arithmetic mean, vertical to layering, harmonic mean, but these are not the best ways to actually approximate the means for these effective permeability situations. We can do this for all phases. We get REV information for all phases, and we can add geological information to the simple guidelines and say, well, what is going to actually happen if you have more of a permeable facies, less of a permeable facies? What is going to happen to effective permeability? So again, you start with a geologically informed input in your reservoir models rather than relying on a measurement of a little core plug where you know that is underestimating heterogeneity. Same for guidelines for KVKH. KVKH, reservoir engineers, is always 0.1. It's actually not 0.1. You can use the information, the geological information, to work out what are reasonably good starting values, reliable starting values for your KVKH values. And we can do this now for CO2 trapping. So in RM, we expanded this to I promise I'm not going to talk too much about RM, but here I am once again talking about RM. So we do two-phase flow upscaling the capillary and viscous limits in RM these days to get some effective relative permeability curves if we want to understand what are the multi-phase flow REV scales and trapping behaviors in the presence of these heterogeneities are larger than grid block, larger than the plug, but less than the grid block. Where do we want to go with this? So really the idea is that eventually we end up building REV-based reservoir models. We have then the different phases. We use the geological information to put in the right bit of geology, including uncertainties, to populate the reservoir model with geologically informed effective properties, not the core plug properties. And then we can use some distance-based global sensitivity analysis to understand which of these properties influence, for example, CO2 storage project, a geothermal project, the most, and what data would we need to narrow down what the properties actually are and to reduce uncertainty. Last time I spoke about the Delft geothermal project. Again, one of the great things is now we're getting data, we can start validating these workflows. So in the Delft geothermal project, we've drilled injector-producer well. Phil Varden is leading this project. The idea is that we're going to heat our campus with geothermal heat and part of the city of Delft with geothermal heat. Everything goes to plan by the end of the year. We're going to start pumping hot water. And one of the ideas is we're going to have the traditional models or REV-based geological models. We run some simulations. And what we would expect that if we put the right geology into our models, we get much better agreement with the production data compared to models that are overly simplistic. So the final thought is a wonderful thing, see the geology like the fluid does. The same bit of geology that we have is going to react differently depending on which fluids we're going to deal with. Mark Bentley came up with this, and he calls it Flores rule, and there's an entire story why this is called Flores rule. For hydrocarbons, so if you have a dry gas system, you really need a lot of heterogeneity for the system, for the geology to start matter. If you have heavy oil or light oil, you actually need very little heterogeneity for the geology to matter and influence your reservoir behavior. You map this onto CCS geothermal. Probably these low enthalpy, single phase geothermal systems, we can get away with much larger REV scales. Heterogeneity is not as important, but the moment we go into the CO2 storage domain, we have multi-phase geothermal systems, hydrogen storage, probably a lot of small-scale heterogeneity will become incredibly important. To conclude, reservoir engineer, know your geology. Stop here, there's some other conclusions. Basically, we do have the workflows, we do have the data, we do have the tools. Let's use them to transition across scales, to build meaningful reservoir models that bring the right geology into the reservoir simulation domain so we can actually develop geothermal energy, CO2 storage, hydrogen storage projects safely, securely, at the pace we need them to make impact on the energy transition. With that, thank you very much.
Thank you, Dr. Geiger. Questions from the floor?
Hi, Professor. I'd like to say that I'm a big fan of your technical papers on fracturing modeling. And about the geothermal system, especially the engineered or enhanced geothermal system, do you believe that the traditional workflows for fracturing modeling can be applied to those systems?
Oh, this is a really, really good, really tough question. I think that what we really need to understand is where the work from Giovanni becomes so important is to understand the fracture mechanics and how fractures open and close, have the right laboratory data. I think numerically we do have the right tools these days to deal with this, but we need the right data. My personal view from EGS is this is a really, really tough part. No, you wouldn't have at Petrobras, you wouldn't have started developing pre-salt from day one. We start with the easy reservoirs and learn from this. And I think this is in terms of geothermal industry. We want to do these easy projects first, learn from them before we go to something that's actually really tricky to stimulate very hard rock or granitic rock, create fractures to get flow pathways that stay open for 40 years. That's a tough, tough challenge. So data, yeah, we can collect it. Simulation tools are there, but I think there's an opportunity to learn from easier projects first before you go to the difficult ones.
Okay.
And thanks for the comment about the papers.
I have a question.
Yes.
Could be a long comment about this one. We really like your third conclusion. Workflows, tools, and data exist. Traditionally, people would have variograms, run geostatistics, build a geomodel, pop into reservoir simulation. I just came back from last month from this image conference in Houston, international meeting for applied geoscience and energy. A lot of seismic companies promoting the fact that they can have new routines with full waveform inversions, really high resolution in terms of looking at the rock and whatnot, and be able to use well logs and core data, limited, and use AI machine learning to populate the model. And I was just quickly thinking about your RRM, that you can sketch the model with seismic, picking the tops and whatnot, be able to use AI machine learning and magnetic field, the gravity, what have you, to actually populate cell by cell, have a more representation, better representation of the geomodel. So perhaps this workflow approach could help expanding the REV to be more representative. Yeah. Is that something that you could look into maybe?
Yeah, so it's a really interesting comment. And the key point I want to make, these are not mutually exclusive workflows. So in the RM world, for example, it's this quick conceptual understanding. If you throw AI in there without conceptual understanding, we're going to be lost as well. But there's certainly synergies in how you then populate properties from a scale up than what we actually measure in the laboratory into larger scale reservoirs. And we need to think about how you do this in an AI framework, but certainly there are some ideas. We have Boris Hespert, who presented the poster last year. There we're playing around a little bit with AI and seismic inversion using RM models to train seismic inversion models that you actually, when you sketch a model, you get immediately feedback of how the seismic would look like to then check what your interpretation, how good does it agree with actually your seismic data. So absolutely synergies. You've renewed us for 5 years, so hopefully in 5 years' time we can present some of these synergies.
Well, that's good. Thank you. Well, it's really good to see that what you're doing could be applied to CCUS and geothermal and oil and gas. So, question here.
Yeah, so this is a comment coming from a geologist. The issue of scaling has been the holy grail. We have data in different scales, from fin sections to logs to seismic outcrop data. So I believe AI, especially with generative AI, might be the only way to resolve the scaling.
Yeah, I think so. This goes a little bit towards what Eli is doing in terms of the fractures and working out what fracture features matter. I think that there is something, we do have the right data. I think we need to look for the common features in the data across scales rather than saying, oh, my outcrop is a little bit different than your outcrop, so I'm going to have a dozen PhD students studying my outcrop in a different way than your outcrop. That's not going to move us further. So using the data that we have, looking for the common trends in the data, that's clearly the way to go.
Okay, no more questions. 2 o'clock. We will take a 15-minute break before the next talk. Thank you, Dr. Geiger.